What's up, everybody? It's Dan from SageMathTutoring.com. It's good to see you all again. This is a review sheet for one of my Pre-Calc students who is in high school. And as many of you know, one of the things that I offer is, like, if you have a review sheet for a test or something like that, and you are stumped on various questions, I can make a YouTube video that takes your literal review sheet and I can solve the questions that you have trouble with. So anyway, clearly the circled questions are the problematic questions in this case. So let's take a look. First, we've got this one, 100 m to the fourth minus 11 m squared minus 9. Okay, so the first thing I see about this is it definitely resembles, in a way, like a normal quadratic expression, you know, something like that. It sort of resembles that in the sense that you have this like descending exponent, and it's also worth noting that at least for this problem, it's not always going to apply necessarily to all these expressions, but the last term happens to be a constant. All right, so I also could see that, you know, if you look at the sign of the exponent that would hypothetically be hovering above the middle variable, it would be 1, and the exponent in the first term is twice that. All right, well, that's actually the same as this scenario. The exponent hovering above the m in this case is 2, and the exponent of this m is twice that. So that is a sign that you might want to do a temporary substitution. Now I'm actually going to write this up here. So we have 100 m to the fourth minus 11 m squared minus 9. And basically, it's helpful to take the middle term, which is, you know, m squared, the middle variable, I should say, which is m squared. I'm going to temporarily call that z. All right. And then what I do is I rewrite this whole thing only with m squared being z. Now let's get very clear about this. If m squared is z, then m to the fourth is z squared. All right, so we're just going to get clear about that. So then we end up with 100 z squared minus 11 z minus 9. And then at that point, it's a matter of just factoring this like it's sort of like a normal situation. Clearly we have a 100 as the coefficient, which might make this a little bit more challenging than if it was just x squared minus 4, blah, 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 blah. But I'm going to do it in a way that I like to do it, which is sometimes called the bomb method. So what I do is I take a look at 100 and I take a look at this number here. So you take a look at the two outside numbers and you multiply them together, and I would get 900 in that case. And then I just look at this number right here. This is the magic number. I ask myself, what factors of negative 900 are such that when I add them together, I get a negative 11? Well, one way of going about this, I mean, 900 has a lot of factors, and negative 900 has a lot of factors. So it's like, you know, you could do like the whole like 1 times 900, and, you know, take into account that, you know, this has, one of them has to be negative, the other has to be positive, or this could be positive and this could be negative. Just keep that in mind. Then you could be like, all right, well, it's like 2 times 450, blah, 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 blah. But the bottom line is, you know, if, like, for example, 2 is positive and 450 was negative, then when you add those, that's going to be like, what, negative 448, right? That's not even close to negative 11. You know that if you were to do this, like, you know, factor list like this, the combination of factors that would end up giving you the negative 11, when you combine them, they'd be closer to the middle, right? They would be closer to the middle. So I think that's important to realize. And at the end of the day, you might notice that 900 is a perfect square. So you know that somewhere in the middle there's going to be like 30 times 30. And when you combine these, like a positive 30 plus a negative 30, or vice versa, that's going to be 0. So that actually gets us closer to negative 11 than, you know, for example, if I combine negative 1 plus 900, that would be 899. That's really far away from negative 11, whereas 0 is at least a little bit closer to negative 11, at least on the number line. So what I would do is I would then sort of explore what's on the outside regions. Is there something that's a little bit less than 30 and something that's a little bit more than 30 that might give me that negative 900? And sure enough, if you sort of thought about it, you would realize that 25 and 36, those two right here would end up giving you a scenario where if, for example, the 25 was negative and the 36 was positive, well, when you combine those, that would be negative 11. All right. So that's a way of kind of going through the motions here without having to actually literally list all of the factors. When you know a lot of the factors that are on the outside are not going to give you the negative 11 that you need, you might actually want to start from the center and then move out from there. All right, a little trick of the trade. I only say that because I'm pretty sure my student can handle that, like, additional layer of strategizing. So what you want to do if you're going to use the bomb method to factor this thing is you're going to rewrite the whole thing. Now, when you rewrite it, you just say plus, and then parentheses, and then z, and then minus 9. So again, rewriting the whole thing, but now you say plus empty parentheses, and then the negative 9. And then what do you put inside the empty parentheses? Well, you put those two numbers that you just discovered would work. All right. So we have 36 minus 25. Now this is, by the way, why they call it the bomb method. Actually, I'm realizing it should be vice versa. We're looking for a negative 11, so I guess I made that mistake before. My student at home may have caught that. So it's 25 minus 36. All right, that's going to give me negative 11. So anyway, you notice how this is negative 11, and we just exploded it. It's almost like negative 11 is like a popcorn kernel in the microwave, and we turn the microwave on, and then it just turns into popcorn by exploding like that. And also notice how I did the plus. This is just a good way to avoid confusion. You just say plus whatever the parentheses is. Now, whatever ends up in here might be a negative number, okay, and that's fine. In this case, it will be a negative number, all right, and that's fine. But you just pause, take a deep breath. Now, the whole purpose of doing that is we're moving things in the direction of factoring by grouping. And the first thing you have to do is take this and distribute it here. Now, we're used to having a number out front and distributing it in that direction, but now we have this variable, and we're going to distribute it in this direction. So that's what we're going to do right now. I'm going to rewrite it on the next line in such a way that represents that move. And here we are. Now, why would we want to do that? Well, the reason we want to do that is because now, if you look at it, we have like a 4-term expression, and sometimes at this level in pre-calc, you can factor out 4-term expressions with the factoring by grouping. All right, we focus on these two first, and then you focus on these two. Now you ask yourself with these, what is the greatest common factor of these? Now, usually with the first two, it's going to be a number and a variable. All right, so just be on the lookout for that. And sure enough, the greatest common factor is 25z. And then you could ask yourself, okay, 25z times what gives me 100z squared? Well, that would be 4z, right? And then you could ask yourself, 25z times what gives me a positive 25z? And that would be a plus 1. All right. Now, we are going to do the exact same over here. All right. You ask yourself, what is the greatest common factor of negative 36z minus 9? Now, if this is negative, then it's going to be a negative in there too. All right. Now, it so happens that it's negative 9. All right. Negative 9. So negative 9 times 4z plus 1. Alright? Now, if you have done things correctly, if you have factored out the proper greatest common factor from these two, it will always, always, always be the case that this parentheses matches this parentheses. Okay? I've even gone so far as to just do this part, right? I'll finish this 25z, and then I figure this whole thing out with these two guys, and then I will immediately just write 4z plus 1 over here with an empty space here, and then kind of work backwards engineer this and be like, okay, well this must be a negative 9 because negative 9 times 4z gives me a negative 36z. Alright, but you know, you have to have massive confidence that you did the first part correctly. Now if you don't like what I just said, just do what I said before, which is to just focus on 2 at a time and then factor out the GCF. Alright, now once you've done that, all you have to do to finish the factoring by grouping is, I think most students, they'll put the 4z first. Alright, 4z plus 1, they'll put this one first, and then you'll have another parentheses, and then the question is, what goes here? Well, what goes here is 25z minus 9. What goes here is literally everything that's left over. Alright, 25z minus 9. Now, for the record, you might ask, well, how did we get from this line to this line? What's really going on there? Well, what you can see, hopefully, is that you actually have 2 terms in this yellow line here. You have one term, a big clump of multiplication, subtracting another big clump of multiplication. This whole big clump of multiplication is itself a term, right? In the same way that 100z squared is a term. This is a term. So it's some term minus another term. Well, guess what? These terms have a greatest common factor. This term has a greatest common factor with this term, namely 4z plus 1. That's the GCF of this and this. So what do? We literally factored it out. Here it is, 4z plus 1. And it's like 4z plus 1 times 25z gives me the first term. 4z plus 1 times negative 9 gives me the second term, right? Because you could always redistribute, and then you'd end up at the top line again. All right? So if that's confusing to you, then just remember the rote rule of simply rewriting. I like to call these parentheses sausage links. Just rewrite this sausage link right here and know that you're going to have another sausage link. And when you ask yourself what goes in this other one, you just fill it up with whatever you didn't put in the first one. All right. So anyway, that's that. However, we are not done yet because m squared equals z and m to the 4th equals z squared. So that means anytime we see a z, we need to replace it with an m squared. So we're going to do that right now. So what we have is 4m squared plus 1, and we have 25m squared minus 9. Now, this is a difference between 2 squares. Difference between 2 squares suggests that, you know, if you have x squared minus y squared, well, that really factors into, you know, x minus y, x plus y. In other words, if you have a perfect square subtracting another perfect square, you could hypothetically factor it thusly. Well, this is a perfect square subtracting another perfect square, because something squared gives you 25m squared, and something squared gives you 9. The thing that's squared that gives you 25m squared is 5m. 5m squared gives you 25m squared, and 3 squared gives you 9. So this right here is going to be 5m minus 3 and 5m plus 3. Now, as far as this thing goes, it's really not much we could do here. It looks like it could be the difference between 2 squares, because this is indeed a perfect square, and actually 1 is a perfect square. But you want to be careful. There's actually no factoring scenario. You know, this is like a factoring pattern. There's no factoring pattern associated with the sum of 2 squares. There's a factoring pattern associated perhaps with the sum of 2 cubes or things like that, but not sum of 2 squared. So we're going to just leave that. We're kind of stuck with that. All right. So that's the full factorization for this problem right here. All right. So looking at the next problem, I think maybe I'll write on the paper right now. Okay, so this looks like it's already perfectly poised for us to do a factoring by grouping. And by the way, I want to make sure actually, are we following the directions? I just assume we're factoring. Yes, factor completely. Okay. So, yeah, so this is already set up for factoring by grouping. So it's like you can take a look at these guys first and then take a look at those. All right. I will nonetheless rewrite this. I'm going to rewrite it right here. Why not? Plus 4x plus 4. All right, so focusing on that, what is the GCF with these two, keeping in mind that it will likely be a number and a variable, and that is true. It's going to be a 2x squared. Okay, so be careful with that, 2x squared. And this ends up becoming just x, it looks like, and this ends up becoming a 1. All right. So if you're not sure, ask yourself 2x squared times what gives me this? Well, that would be x. 2x squared times what gives me this? Well, that would be 1. And then over here, this would definitely be 4, all right? Now, it is a positive 4, so you just write positive 4, all right? You just write that, and positive 4 in the form of plus 4. So we have x plus 1 once again. We know we're on the right track because this matches this. And then once again, using the strategy that we just talked about, you end up with this. All right. Now, for my student at home, please, please, please be on the lookout. Most students would think that you're just done. All right. In the same way that maybe most students would have thought that they were done with this one, and they didn't take into account the fact that, number one, you had to substitute m squared back in for z, and also some students would not have taken into account the fact that there was a difference between two squares to contend with for this one. Well, a lot of students are going to not realize that there's actually another thing that you can factor out here, and that's a 2, okay? Because this term has a 2 as a factor, and this term has a 2 as a factor. So you could actually, I'll leave the, x plus 1 here. Let's imagine we factored out the 2 kind of obnoxiously right there, and this becomes x squared plus 1, reminding ourselves that this is not a special pattern. If it was x squared minus 1, then guess what? We could factor it even more, but it's not. Now, it's kind of awkward to have the 2 in between these. Let's have the 2 out front, and then we will call it a day because there's nothing else we could do with this. All right. That is all she wrote. The only other thing I could think of is maybe the teacher would want this term first because it has an exponent. And when I say first, I mean like right here. You almost always have just like some constant out front. That's going to be true. So maybe you could write it. Honestly, I think this is small potatoes. So for my student at home, don't worry too much about this, I don't think. But that's kind of just nicer looking with the descending order. Something to think about. All right, so that is how you do that one. All right, next page. What do we got? Well, let's start with 33, I guess, right? And let's make sure we are following the directions. Name each type of equation and solve. Remember to check for extraneous solutions when necessary. Right. Okay. So I decided to bring in this chart over here because one of the things that apparently the teacher wants is to name each type of equation and solve, right? And we're going to check for extraneous solutions when necessary, so we can worry about that part later. But there is the part of naming the kind of equation first and then solving it. And, I think this chart is going to be helpful, at least for the first one. Basically, so I hope my student understands. Let's look at the chart real quick. So first of all, you can classify equations by the number of terms they have and the degree, namely the highest exponent. The degree means the highest exponent that's represented. So for example, if I had x cubed plus 2, well, you always actually start by mentioning the degree, okay? At least for something like this, a polynomial like this. And that would be a cubic because it's got a degree of 3. A cubic, and it's a binomial because it's got 2 terms. Binomial because it's got 2 terms. All right. So if the degree is 0, it's a constant. If the degree is 1, it's linear. If the degree is 2, the biggest exponent is 2, it's called quadratic. Be careful because quadratic, the word quad might sound a little bit like 4, like quadrant, but it's not. Quadratic has to do with an exponent of 2. 3 is cubic. 4 is quartic, right? 10 you're not going to need to worry about, so just trust me on that. 5 is quintic, all right? Monomial, binomial. Okay, so if you have one term, it's monomial. If you have two terms, it's a binomial. If you have three terms like that, it's trinomial. Four terms, at the point 4 and above, we just call it a polynomial. All right, so we don't really worry about that, but you should probably know monomial, binomial, and trinomial. Fairly easy to remember, right? Let's see. Okay, the constant term, that's like literally, here's an example. Y equals 12. That's an leading exponent of 0, because think about it. Y equals 12, that's really like 12. Y equals 12x to the 0, right? All right, so that's how that works. Now, this chart, honestly, really only applies, unfortunately, to this first guy. We are going to have to come up with some different names for these three, but nonetheless, let's check out what's up with this. First of all, it is definitely a cubic polynomial. All right, cubic because the largest exponent represented is 3, and a polynomial because we have 4 terms. Right. So believe it or not, we don't need this anymore. So let's just get cracking with this problem. So we have 0 equals 6x cubed plus 19x squared plus 2x minus 3, and once again focusing on 2 at a time, right? It's already in descending order, so we are good to go. So let's see, we have well, actually what we have is a scenario where we cannot factor by grouping. So that means the teacher is being very tricky and giving us a problem that requires us to use the rational root theorem. All right, and the rational root theorem is an additional way of sort of rooting out, well, no pun intended, rooting out what the roots might be, the rational roots might be. And what do we mean by roots? First of all, let's make sure we're clear about that. Roots are the values of x that would cause the whole thing to be 0. In other words, the roots would be the answers in this case. What does x equal? That would cause this whole thing to be 0. And for the record, if you were to graph this thing, the roots would end up being the places where the graph intersects the x-axis. All right, so just a little terminology for you. And in order to do it, what you do is you take all the factors of like this term, and then this term, the 6, the -3 and the 6, and you just analyze each separately. So it's like -3, definitely like going to be positive or negative 1 and 3. No question about that. That is all of the factors for -3. And then all the factors for a positive 6, well, that would be plus minus, let's see, clearly 1, 2, 3, and 6. And you just kind of get clear about that stuff. And then what you're going to do is you're going to figure out all the different combinations where this would be the numerator over, this being the denominator. So we can kind of do that off to the side. All right, let me just move this over here, actually. And I'm going to actually erase these annoying lines. So what we could do off to the side with this information is recognize that the possible rational roots are going to be plus minus, 1 over 1, which is just 1. It's going to be, let's stick with one denominator at a time, 3 over 1, which is just 3. And then we have 1 over 2, which is 1/2. And then we have 3 over 2, which is 3/2. And then we have 1 over 3, which is 1/3. And then we have let's see, what is it? 3 over 3, which is just 1. We already mentioned that. Then we're going to have 1 over 6, which is 1/6. And we're going to have 3 over 6, which is 1/2, and we've already mentioned 1/2. So here we go. Keep in mind that it is the plus minus version of all of this stuff. Once again, I just, treated these like the numbers in the numerator. I treated these like the numbers in the denominator, and I just did literally every combination of what could be, and I was just meticulous to not repeat numbers. For example, 3 over 3 was just 1. I already had a 1, so we don't need to write that down again. Anyway, so these are all the rational roots. One way of moving from here, and I'm really hoping that this is the way that my teacher taught my student, because it's a pretty good way once you get the hang of it. And if my teacher did not teach my student this way, then what I'm about to say is probably going to be fairly confusing. But let's go for it. So you could use synthetic division for this part, where basically, like, you could try the positive and negative versions of these numbers and see if after using synthetic division you end up with a 0 as the remainder. So here I go, setting things up for synthetic division. Now, let's keep in mind the 6 corresponds with this coefficient, the 19 corresponds with that, the 2 corresponds with that, the -3 corresponds with that. Now, keep in mind there's a perfect descending order of exponents here. It goes 3, 2, 1, and then actually 0 right there. Had we been missing one of these, like, exponents in the chain of descending exponents, like for example, if there was no 19x squared here and it just went from 6x cubed and then the next thing was 2x, just keep in mind that you'd still have to represent a placeholder for the x squared term, even if there wasn't an x squared term. So you would literally write 0 there, all right, because it would be like 0x squared plus 2x minus 3, all right? We're, in a sense, lucky that the teacher gave us a problem where there is this perfect descending order, all right? But either way, when you're doing synthetic division, you have to represent all the potential coefficients, even potential coefficients for whatever the x term would be if the exponents were in descending order. Anyway, I'm hoping my student understands that, but nonetheless, here we are. Let's try out 1 as a first thing that we could do. So it's 6 drops down immediately. By the way, that's always going to happen. Okay, 6 is going to drop down. So 1 times 6 is just 6. 19 plus 6 is 25. 1 times 25 is 25. Now I can already tell, this is going to be 25 plus 2, which is 27. This is going to be 27 over here. And when I combine these guys, I'm not going to get a 0. Basically, what we're trying to figure out is whatever number over here would result in a 0 over here. That's what we're trying to figure out, right? So clearly, 1 won't do it because we're going to end up with a 27 over here. All right. Now, once we find a number over here that gives us a 0 over here, then we know that that is one of the rational roots. Okay. That's the philosophy we're operating on. So I'm actually just going to leave the 6 down there, actually, because 6 is always going to be there anyway. And in fact, I'm going to leave the arrow too. So what about -1? What if we had -1? Well, -1 times a positive 6 would be a -6, right? And this would be 19 minus 6 is 13. This would be a -13. This would be a, looks like a -11, unless I'm making a careless mistake. And this would be a 11, and that doesn't do it either. So we have to, unfortunately, move on to a different number. So we tried +1 and -1. Now we're going to try 3. I have a feeling -3 might do it. Let's try -3 first. So -3 times 6 is -18. And then we're going to have 1. And 1 times -3 is -3. And then we have -1. And then we have a 3. Bingo. Look at that. Ding, 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 ding. Right? Look at that. -1 times -3. -3 times -1 is +3. And there we go. So believe it or not, we have a rational root on our hands, which is a beautiful thing. Now, why did I say, I was like, let's do 3. Why did I say, I have a feeling about -3? The reason is because with the way that these are going, like, I've noticed that if this is positive, like if positive 1 was up here and that blows up the 6 and then it blows up a number, positive 1 resulted in this blowing up to a 27 over here. So I'm a little bit weary of the positive numbers over here, because if positive 1 blows it up to 27 over here, or whatever the hell it was before, then positive 3 is really going to blow it up to something crazy. So I'm just like, all right, let me just focus on the negative numbers first. So it turned out to work out. So we have negative 3, and then we have 0. Okay, let's see. So we know for a fact what this literally means is that one of the factors, one of the roots, is negative 3. All right? Now, what does that mean when we like factor this big debacle? You know, imagine we wanted to factor it. Well, basically what that means is that this guy could be rewritten and factored as this. Now you want to be careful with this. It's going to be x plus 3 times something else. All right. Now, x plus 3, why is that? Because if negative 3 is a root, well, that means that, you know, if this was a negative 3, it would be a negative 3 plus 3, right? And that whole thing would be a 0. And then it would be 0 times whatever the hell this is, and that would equal 0. Now, we know what this is, okay? This is corresponding with these numbers, because the largest exponent over here was a 3, so when you kind of look at this, as long as you have this like remainder of 0 especially, you can look at these 3 numbers and just know that basically what this is symbolic for is 6x squared plus 1x minus 1. Okay, that's what this is right here. Okay, and notice the corresponding numbers with the coefficients. Okay, so that is literally what's over here. All right, and what we could do from there, what I like to do at least, is then to just use either factoring, like regular factoring over here, or maybe even the quadratic formula if need be, because the bottom line is if you could factor this into, like, imagine you could factor it, well, you factor that into 2 different sausage links, well then you know that the root would be easily found by looking at x and the number, and the root would be easily found here. I'm not exactly sure it can be factored yet. Let's see. If I was to use sort of the method that I was suggesting before with multiplying these guys, that gives me a negative 6. Are there factors of negative 6 that when added together would give me a positive 1? Well, absolutely, actually, which is great. That's going to be 6x squared plus, remember, empty parentheses, I mean the negative 1, that's going to be 3 minus 2, right? And then once again I'm going to distribute that, and then I end up with 6x squared plus 3x minus 2x minus 1. Factoring by grouping now would result in me saying 3x times 2x plus 1 minus, it's really a minus 1 here. I'm actually going to write that even though it's kind of sloppy looking. 2x plus 1. Now, what prompted me to write the minus 1? Well, I knew that this whole thing, I needed to get the same parentheses over here. So I immediately in my head asked myself, okay, I want 2x plus 1 to be in parentheses over here. So what is the factor that I need out here? Well, that's clearly going to be a negative 1. And then on the next line, you know, once again, preserve the sausage link and then fill up the other one with all the other stuff, right? So that is a beautiful factorization for 6x squared plus x minus 1. So what that means for us at the end of the day is that it's kind of unusual for me to go upward with it, but we still have the x plus 3 equals 0, right? And then now we have these other sausage links that say 2x plus 1 and 3x minus 1. Now, let's focus on these guys. Could we have continued with the rational root theorem and just plugged in this case, negative 1/2, and in this case, positive 1/3 over here, and discovered that they would have been roots as well? Well, the answer is yes. But in my opinion, and this is just me, so for my student at home, I would sort of defer to whatever the teacher seems to suggest. The way that I learn this is to use synthetic division to find the first rational root, and once it steps down to a little bit more of a familiar looking equation, where it's like 3 terms that we need to contend with now, well, we're really used to that by now. I mean, that's just 6x squared plus x minus 1. I'd much rather just factor that to find the other 2 terms rather than keep checking all these different numbers, because that's, like, in my opinion, pretty tedious, all right? And that's what we did, and here we are, okay? Now, in my opinion, it's, like, very easy to know what the roots are. I mean, in fact, we already figured out the first root is negative 3, but we also know that negative 1/2 would work. We also know that 1/3 would work. Now, your teacher made the point of saying check for extraneous solutions. Okay? So my thought is you might want to plug in each of these back into the equation. All right? And just double check, make sure that they work. All right? I think that's what she means by that, or he means by that. You might want to take your answers, plug them back in, make sure that they work. All right, so that's that one. Okay, looking at number 35, which says that 20 is equal to 10 to the e to the 5x. Well, first of all, that is an exponential equation. And the way that I know is because the variable that we're trying to solve for is in the exponent. All right. Now, if you're dealing with an ugly thing like this, number one, don't get thrown off by the e. That's just a famous number like pi, and it's a number. It might look like it's a variable, but it's not. Think about it. Pi is not a variable. Pi is like 3.14 blah, 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 right? So it's the same thing with the e. And let's dive in. When you have something like this, what you want to do is most definitely isolate the base that has the exponent in question. You want to isolate that by itself. So clearly the 10 is in the way. That's very easy. We just divide both sides by 10, and we end up with e to the 5x equals 2. Okay, then the question is, all right, what do we do? Because, like, how am I going to bring this 5x down to earth and so on? Well, the trick of the trade with this, and I'm going to sort of rewrite it as follows because you'll see in a moment. All right, by the way, this is just the same thing, okay, but I'm drawing this nice space here. The trick of the trade is to recognize that, okay, well, if I have this e, well, the sort of inverse of e is the natural log. So I'm assuming my student recalls that you could do the ln, the natural log of both sides. All right, and you're going to understand why in a moment. But I want to first explain the fact that we can do this, okay? We can do this because you can do anything you want to this equation, or to this side, as long as you do it to this side. You could multiply e to the 5x or perform any operation on e to the 5x, you know, that you want to, as long as you do it over here, right? Well, we're sort of, you know, dropping the natural log on this side, and we're going to have it over here too. So we're taking the natural log of e to the 5x, and that's okay as long as we take the natural log of 2. Okay? Now, why the hell would I want to do that? Well, one of the things you might notice that you might remember from, like, the properties of logarithms is that when you do ln e to the something, then you end up being able to just literally have that something represented on that side, and then we have ln2. Now, should I explain that? Yeah, I'll explain why. All right, so, okay, there's a few reasons why. Number one, ln of, let's say, well, we'll just go with ln of e. Let's start there. that's secretly the log of e, right? The log with a base e, right? And, you know, ln e, what does that equal? Well, that's code for e to the what power equals this. E to the what power equals this. Well, clearly, that is going to be 1. All right, 1. So at a certain point, it might be worth memorizing that ln e is just 1. That's one thing that you could sort of get in your head. There's another thing that you get in your head that says that the properties of logarithms, let's say we were dealing with a log x to the 3rd power, where it's like you have this exponent of 3 hovering above just the x, right? Well, you could rewrite that as 3 ln x. There's a property of logarithms in general. Let's say you could take this exponent and swing it out front and turn it into a coefficient. So in a way, if you look at this ln e thing over there, let's analyze ln e to the 5x. Well, couldn't you kind of bring the 5x out front? I mean, why the hell not, right? According to that property we were just talking about. It ends up becoming 5x, I'll do this in cursive, 5x ln e, right? And we already discovered what ln e is. Over here, it's 1, right? So this ends up becoming 5x times 1. Obviously, that's just 5x. All right, so that's the explanation as to why, if you do ln e to the blah, it just becomes that. Now, do you have to do all this in the future? No. You could actually literally just memorize that if you take the ln of this thing, it drops the exponent down. All right, so that's where we are right now. And then we could be like, all right, well, dividing both sides by 5 would give me ln 2 over 5. Now, here's the deal for my student at home. I'm not going to do it because I'm trying to move quickly. You could plug this into your calculator. All right, ln 2 is something to plug into a calculator. Divide it by 5, right? And that should definitely work as the answer. Okay. If you want to double check and plug in ln 2 over 5, if you're going to plug it back into the calculator, I would actually plug in this number rather than the decimal equivalent. All right. If you plug in the decimal equivalent here, here, you're probably going to be like 10 times e to the decimal equivalent is going to equal like 19.9999. Maybe it'd be something like that. All right, so just be on the lookout for that. Anyway, I hope that's clear. Let's move on to the next problem. So, 3 log blah, 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 blah. Let's take a look at this. X plus 3 equals 5. Okay. So, there's another property of logarithms. Actually, am I going to be able to use that? Let's see. I am curious as to what happens when I divide both sides by 3, because I'm curious to get this log thing by itself. Let's do that first. Log x plus 3 equals 5 over 3. Okay, I think this is just a classic rewriting of this into the exponent equation, because remember, there's a little 10 under here, because if there's no mention of the base, that means that it's secretly a base of 10. And remember, for my dear student at home, it's like 10 to the this power equals this. I literally think of like a weird triangle shape where it's like 10 to the this power equals this, right? With these, arrows. I'm going to rewrite it that way. 10 to the 5/3 equals x plus 3. Now, obviously, we're a little, maybe confused by the 5/3. I mean, we could, of course, just rewrite that if we had to as the cube root of 10 to the 5th. I mean, that's a way to go. And then we have x plus 3. But the thing is bottom line is, I mean, we are perfectly poised to solve for x right now. I mean, it's great. All you have to do is subtract 3 from both sides. So I'm actually going to keep it as 10 to the 5 thirds because that'll be fairly easy to plug into your calculator actually. So it's going to be 10 to the 5 thirds minus 3 equals x. And that is something you definitely plug into your calculator. Just be careful when you plug into the calculator 10 to the 5 thirds, you know, make sure the 5 over 3 is in like parentheses, right? When you're like 10 upwards arrow, 5 over 3 in parentheses, and then subtract 3 from that, and that should be the answer. All right, so that is that one. All right, looking at problem number 39, we have 2 to the 4x minus 1 equals 3 to the 1 minus x. Okay, so, well, I mean, this could be rewritten as 2 to the 4x all over 2. And this could be rewritten as 3 all over 3 to the x. Does that help our cause? That does not help our cause, so I think we're going to have to bust out the logarithm trick of the trade, where we take advantage of that property that I was talking about before, where it's like the exponent could be brought to the front of the log. So imagine we just rewrote this, or on the next line called it log of 2 raised to the 4x minus 1, and that equals log of 3 raised to the 1 minus x. Because now we can bring this out front, we can bring this out front. So that's going to become 4x minus 1 times log of just 2. And that's going to equal 1 minus x times log of 3. Okay. I'm now tempted to distribute the logs into the parentheses, so this becomes 4x times log 2 minus log 2, and that equals log 3 minus x log 3. So the reason I do that is because I know that this is like a log 2 and it looks like this is some fancy schmancy thing, but just keep in mind that's actually a constant, right? This is a constant. It's just some number. Log 3 is just some number, and now we have two terms that have an x in it, right? And at the end of the day, we're trying to solve for x. So as usual, you take note of the terms that have an x in it and just get them on one side, and you take all the terms that don't have an x in it and you put those on the other side. I believe that that should work. So let's add x log 3 to both sides, and you would end up with 4x log 2 plus x log 3. And we're going to add log 2 to both sides, so we would end up with log 3 plus log 2. Okay. So, you know, these are the constants, and these are the terms that have x in it. And the reason I'd want to do that is because I can now actually factor out the x, right? And we end up with 4 log 2 plus log 3 equals log 3 plus log 2. And let's actually, we'll continue to just focus here. Now we can divide both sides by this whole thing and isolate the x. So we'd end up with x equals log 3 plus log 2 all over 4 log 2 plus log 3. I do not see any opportunities to make any cancellations here. I mean, I know this log 3 plus log 2 sort of resembles log 3 plus log 2 over here, but there's this 4 that's in the way, so there's no real, like, cancellations that could be done. Plus it's just addition, you know, between everything. I mean, if it was multiplication, log 3 times log 2 and log 2 times log 3, well, certainly you could cancel there. I am fairly certain, unless I made a careless mistake, which is always possible, I'm fairly certain that this is the answer. It's possible the teacher might let you leave it like this, but it's also possible that you might have to actually just plug this stuff into the calculator, and then you would get your answer from there. Okay, final problem. Let's see. Write the following as a single log and simplify if possible. Okay, so this is like consolidating, or I don't know, maybe there's a better word for it, but you know, it's the opposite of expanding, that's for sure. So this really just is one of those problems that sort of tests your ability to recognize the utility of this property, where you could expand this to become that, and vice versa. You could consolidate these to turn it back into that if you had to. There's also another property that says, you know, if you have like this, log of x over 2, well, that could turn into, hypothetically, log of x minus log of 2. All right, so these are the properties that I think my student for sure has had to grapple with recently. Before I dive in, I'm just going to look at it. Write it as a single log and simplify if possible. So there's certainly addition happening. Yeah, so I'll just write it down for now. So that is a big crazy log thing. So that's 1/3 plus log 8 minus log 6. I love this logo, but it gets in the way. So plus 2/3 log 125. Okay, so I think the first thing that stands out to me is that there's a 1/3 in front of this thing, and there's a 2/3 in front of this thing. Now, the 1/3 is not being applied to like the whole thing. You know, if there were like brackets around this part, well, then the 1/3 would be applying to all of this. But it so happens that there are not brackets. Okay, there are not brackets, which means that that 1/3 is only getting applied to the first term, right? So my first thought is, right away, let's bring this 1/3 out front and use that to hover over the 343, because that's the exponent of 343. And we're going to do the same thing with this 2/3 and the 125. Now, part of my motivation kind of has to do with PEMDAS, actually, because it's like, you know, you want to kind of deal with exponents first. So this is an exponent scenario, right? So it's 1/3. It's going to be 343 raised to the 1/3. Part of my motivation also has to do with the fact that raising something to the 1/3 power, like 343 raised to the 1/3 power, well, that's really the same thing as taking the cube root of 343. Raising something to the 2/3 power, well, that's really the same thing as taking the cube root of whatever that number is and then squaring the result. Okay, so nonetheless, let's write that. 343 raised to the 1/3 power. And I'm going to go ahead and just rewrite the rest of this stuff. Okay, we'll take it one step at a time. Let's not get ahead of ourselves. Now, in your calculator, you could always raise 343 to the 1/3 power, and that would give you 7, actually. So we end up with log of 7. Look at that. Simplifying already. So that's going to be plus log of 8 minus log of 6. And what is it? Plus log of 125. Okay, well, let's figure out 25 raised to the 2/3, or 125 raised to the 2/3 is going to be something nice too. That's definitely going to be 25, all right? So that's 25. Now from here, we can go from left to right. And another way of thinking about it is anytime you're subtracting something, like whatever that number is, it just gets shoved into the denominator. Okay, that's a way of thinking about it too. In fact, I'm going to rewrite this in a way that, in my opinion, will be less confusing. What you might want to try to do is just get all the additions first. This is not really necessary, but you might want to just get all the positive logs first, just to sort of organize it at a higher level, and to recognize that, you know, since it's addition according to the properties of logarithms, we're going to be multiplying the 7 times the 8 and the 25, and then this 6 is going to be in the denominator. So this ends up becoming log of 7 times 8 times 25 all over 6. All right, so that's a way of thinking about it. And at the end of the day, I'll just do this, whatever. That is going to become, let's find out, a decimal, 233.333. 3 repeating. That right there is a 3 repeating, even though it doesn't look like it. I'm pretty sure that's correct right there. I could have, of course, made a careless mistake somewhere along the way, but I think what's most important is understanding the principles. Quick recap. Get these coefficients, hover them above the 343 and the 125 as exponents. Since the directions literally said to simplify, don't just combine the logarithms, but actually simplify it. Well, we want to simplify it. You know, who wants to deal with 343 to the 1/3 power? We turn that into a 7. We turn the 125 to the 2/3 power into a 25. Then you have a nice string of, you know, addition and subtraction. I didn't really have to do the next part, but I put the additions first and the subtractions next to really showcase the fact that, yes, it's going to be 7 times 8 times 25 up top, and it's going to be this lonely 6 down below because of the negative, right? I'm going to expect my student to sort of understand those properties of logarithms. I had briefly touched upon the property of logarithm that says, you know, expand. You know, if you have multiplication, that means you expand it. If you have division, that means it's a subtraction scenario. Again, I already touched upon that. Anyway, I believe that this should suffice for my student. You know, so for my student who's watching, good luck on the test. Not easy stuff. It's a lot of different concepts, but you might want to practice a couple other problems in your textbook before you know, just assume that you're ready. Maybe like at least 3 problems, you know what I mean? But hopefully this video was helpful. And for those of you who are watching who are not my student, maybe it was helpful for you guys too. Anyway, if I made any mistakes, actually, comment below. Let me know if I made mistakes. And we can all work as a team when it comes to this stuff. Anyway, take care.